In this video, we're going to look at the various factoring techniques, including when and how to use each specific one. First off, I cannot emphasize enough how important it is, especially for those of you who may have struggled with factoring or just don't remember it that well. It's very important for you guys to check your answers, at least until you get comfortable with the process, because it's very easy for you to take your factored form and multiply the numbers back together. If you end up with the original expression that you were originally factoring, then you know you did it correctly. So it only takes a matter of seconds to check your answers. I highly recommend it for those of you who struggle with this technique. Here I have a quick chart to show you when you should try the different methods. The first one at the top of this tree of sorts I've made is the GCF. And you'll notice that I've written the restriction here. It doesn't matter how many terms are in the polynomial for you to use that method. Also, the reason I've put it at the top and then I have the arrows coming down, this should always be the first technique you attempt to use. Many times you'll use the GCF factoring technique and then you'll also use the difference of squares. This makes the second step of the factoring a lot easier though, as long as you do this one first. So check for a greatest common factor and then look at how many terms are left in your polynomial. If it only has two terms, which we usually call a binomial, then you only need to worry about the difference of squares or the sum and difference of cubes. So these will only come into play if you see things to the second or the third power. Also, if it's three terms, we usually call this a trinomial. There are two different cases here. The first case I'll show you, this is the one you guys are most familiar with. You're just finding the two numbers that multiply to c and add up to b. The second trinomial, it looks very similar, but when you have a number in front of the x squared variable, it does make the factoring a bit more complicated. So it's usually a bit more of a guess and check approach whenever that happens. So look for either of these cases when you have three terms. And then when there are four terms, there's only one technique for us to consider, and that's called grouping. So now we'll look at each of them in more detail. The first and most important factoring technique is what we call the GCF, for greatest common factor. The process is pretty straightforward. You just write the greatest common factor, or whatever each term has in common, outside of a set of parentheses. And then you have inside of the parentheses, you divide each term you had by the GCF you factored out. Whatever's left is what goes inside the parentheses. So find what they all have in common, divide that out from each term, what's left goes inside. Comments about this one. You should always check for this factoring technique first. Don't go into the difference of squares and things until after you've tried to do the GCF, because it will make the other factoring technique work a lot easier. It'll give you much smaller numbers to work with if you do this one first. And the other technique, which I also mentioned on that last slide, this one, it doesn't matter how many terms are in the polynomial. So you can have 2 or you can have 8. There still might be a GCF that they all have in common. So here are a couple quick examples finding the GCF. You'll notice on number 1, we have 2 terms. The first thing I like to do is I like to focus on the numbers and the variables separately. So if we're just talking about the 6 and the 9, the number that both of those are divisible by, the greatest common factor, is 3. And then separately, I like to look at any variables. We have n to the second power and n to the first power, so they both have an n to the first power in common. And then inside of the parentheses, we're going to divide 6n squared by 3n. Again, I focus on the numbers and the variables separately, so 6 divided by 3 is 2, and n squared divided by n is n. Next term, we have plus 9 divided by 3 is 3. And n to the first divided by n to the first cancels. So that is our factoring. We have 3n times 2n plus 3. And to check your answer, like I said, you would just multiply this back out. So 3 times 2 is 6, n times n is n squared, that checks. And 3 times 3 is 9, n times no variable is n, so 9n. Second quick example, I'm going to focus on the numbers again first. So everything here is divisible by 3. And for the variables, we have the third power, the second power, and the first power. So the biggest exponent that they all have in common is the first power. So that's our GCF that we've pulled out. And then we divide. 3 divided by 3 is 1, but you don't need to write 1 times something, so I'm just going to leave it off. Y to the third divided by y to the first is y squared. And then go to the next term. 9 divided by 3 is going to be a positive 3. And then y squared divided by y is y. Next term, still a plus. So 15 divided by 3 is 5. And then the y divided by y cancels out. And so what usually happens is you'll take out the GCF, and then you might still be able to factor what's in here a little bit more. In this case, there's nothing else we can do, so this example is done because all I wanted to show was the GCF process. But remember, please, 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 if you're struggling with this, keep checking your answers until you really get the hang of this and feel comfortable doing it without needing to check. The next technique comes up whenever you see things raised to the second power, and it only works when you have two terms. So if you have something in the form a squared minus b squared, then you can break this down as a plus b and a minus b. So comments to make here, it only works for a subtraction sign here. That's the first bullet. There is no such thing as the sum of squares factoring, so it has to be a minus sign for you to do this. Next, it only works when there are two terms. You have to have this term minus this term. Still remember to take out the GCF first if possible, because that may make it easier to do the difference of squares formula as the second step. And don't forget to take the square root of what you have for the a squared and b squared. That's what it's indicating. Like if you have x squared here, then for your factored form, you're going to have x plus something and x minus something. If it said minus 4, then you're taking the square root of 4, so you would have x plus 2 and x minus 2. So don't forget to take the square root of these two terms for writing your a plus b and a minus b pieces. Something you may find helpful in the beginning is to just go ahead and write the square root of each of the two terms above the numbers. So the square root of x squared is x, and the square root of 25 is 5. And that way I can make sure that I correctly identify my a and b values before I set up the a plus b, a minus b. All right, so since I have a minus sign here and there wasn't a GCF to factor out first, I'm going to go ahead and write out my a plus b and then a minus b separately. One comment on the order of these two binomials, the order does not actually matter because for multiplication, 2 times 3 is the same as 3 times 2. So the order that you're multiplying two numbers does not change your answer. So if you want to flip that, you can, feel free. Next one, this one, again, it's going to be helpful to write the square root above just to get the hang of this. So the square root of 25 is 5, and the square root of y squared is y. So my a value is going to be 5y, and that's why I like to write this above, especially when you have a number and a variable combined. Square root of 36 is just 6. I know I can use this technique because I was able to take the square root of both terms, the two terms I have, and it's a minus sign in between. So our answer for this one is just going to be 5y plus 6 and 5y minus 6. Remember that you can check your answer by multiplying these back out. So if you FOILed this, you would have 5y times 5y is 25y squared. The outside and the inside products should cancel in this case. And 6 times negative 6 is negative 36. So that's why I know that this is the correct factoring here. This next technique is actually very similar to the last one we looked at. The main differences here are that we do have both a sum and difference form of it. And the other important thing is that now we're dealing with terms to the third power. So instead of taking the square root of both terms, take the cube root or the third root of both terms, and then you can just plug those numbers in for the a's and the b's. Again, this technique only works for expressions with two terms. I do still recommend finding the cube root first to identify what a and b are so that you can plug in more easily. And then if you memorize the a squared, ab, b squared part, because that's the same for both, you can use the acronym SOAP to help remember when to write a plus and when to write a minus. So the way this works is if you're dealing with the sum of cubes formula, then we have a plus sign here. So same sign for the first one, opposite sign for the next one, and the last one is always a positive. So whether you start with a plus or start with a minus, the same, opposite, always positive helps you fill in those plus and minus signs. So here I've already written the cube root of our numbers. X to the third power is x cubed and 2 to the third power is 8. So the breakdown from the last slide is a, b, and then a squared, a times b, and b squared. In fact, I can do that for this one as well. So I have a, b, a squared, a times b, and b squared. So that breakdown is the same whether you have a plus or a minus in the question you're working with. And then to remember the signs, just use the acronym SOAP. So this one has a plus, same sign, opposite sign is that, and then the last one's always a positive. And if we were dealing with a difference of cubes, the same sign is now a minus, the opposite sign is now a plus, and the last one is always a plus. So that same opposite, always positive, works for either the sum or difference of cubes, as long as you can also remember the a squared, b squared part. I will also add that I see a lot of people try to factor down these trinomial pieces more, but it actually can't be done. So when you use the sum or the difference of cubes, this is the most factored form. You cannot break down that trinomial any more than what is already shown. Now we're going to look at the easy trinomial factoring. The easy case happens whenever you do not have a number in front of the x squared. So the way this works is you find the pair of numbers whose product is in this C spot, number by itself, and the sum of those two numbers is B. And the two numbers you pick, the ones whose product and sum make this B and C value, I'm going to use the numbers m and n, or the variables m and n, to represent this for a second. You just write the factored form as x plus m and x plus n. Again, the order in this case doesn't particularly matter. Just be careful with the plus or minus signs to make sure things multiply and add correctly to the given numbers. Please do not confuse this with what happens when there's a coefficient in front of x squared. That's the next technique we'll look at. And don't forget that you can check your answer by just foiling this back out to make sure your answers work the way you expected. Since neither of these examples have a number in front of x squared, I already set up my two binomials as being x and x for both of them because those parts aren't going to change for this. That's what's nice about the easier factoring trinomials. So now you just need to think about numbers that multiply to 12 but add up to -8. So in this case, I'm going to pick -6 and -2. Now there were other numbers that multiplied to 12, but this is the only possible pair that also added up to -8. So -6 times -2 is 12, -6 plus -2 is -8. That's why this is the correct factoring. And then again, FOIL this out to check your answer if you need to. Here again, I need to pick two numbers that multiply to the last number. So a negative, that means I'm going to have one plus and one minus this time. And then I need those numbers to add up to a +2. So I'm going to pick 5, +5, and -3, because if you multiply those numbers together, you get -15, but if you add those numbers together, you get a +2. Now for the harder case, when we do have a number in front of the x squared, basically you want to list out all of the factors of this first number and the factors of this last number separately. And the factors of the ax squared piece are going to be the first numbers in each binomial, and the factors of this last number will go in the last spot of each binomial, the second spot in each set of parentheses. And then basically you just want to keep guessing and checking from the pairs that you're picking until you get one that foils together and correctly gives you the original expression. It's very important to check your answer on these because this is the easiest one to make a mistake on. Think that your numbers will multiply or add correctly, but find out that it doesn't actually work on. So this is what I meant for step 1. Take whatever this first term is and find all the different possible factors of it. So it could be 4x times x, or it could be 2x times 2x. These are the possible terms that I'll be writing for the first part of each binomial. And then the factors of this last term, this 3, there's only one pair of factors for this. It's got to be 1 times 3. So then you just pick one of the factors for the first term and you write them in. And then you pick one of your pair of factors for this second piece, the last term, the c value, and you write them in somewhere. And then make sure you think about whether they're going to be pluses or minuses. And then you have to check your answer, because if that possible combination didn't work, then you might want to flip. You might want to put the 1 here and the 3 here instead. Or maybe instead of doing 4x and x, maybe you want to pick the 2x and 2x for your first terms. So you write out all the factors, make a guess with it, and then check your answer. 4x times x is 4x squared. And then 4x times 1 is 4x. 3 times x is 3x. And 1 times 3 is 3. So if you combine the like terms here, we end up with 4x squared plus 7x plus 3. So that's how I knew that this was the correct factoring. This is just me checking my answer, but that's how I know I put the right numbers in the right spots for my breakdown here on number 9. So again, I've written my factors of the first term. The only way to get 3x squared is to do 3x times x. And the only way to get 6 is by doing 1 times 6 or 3 times 2. So I don't have many choices for the first part of each binomial. I can just go ahead and write in the 3x times x. For the second number in the binomials, I do have choices. I could either pick 1 and 6 or I could pick 3 and 2. So in this case, I'm going to pick the 3 and 2 combo. And the more you practice this, the better you'll get at making the guess correctly the first time. I know that I need the numbers to add up to a negative, so I want a bigger number for the negative product and a smaller number for the positive product. So by putting my plus and minus signs this way, I end up with minus 9x plus 2x if I FOIL it out. And my last product gives me the negative 6, and my first product gives me the 3x squared. So that's how I know that this is the correct choice. Remember, if you picked the wrong numbers, like 1 and 6, or if you put 2 and 3 in the wrong spots, then when you FOIL this out, it will not match your original expression. That's okay. Just do it again and try different numbers or rearranging the numbers until you get one that checks correctly. The last technique we're going to look at is called grouping. This one only works when you have 4 terms in the expression. So basically, this is just doing the GCF multiple times. You take your 4 terms and you look at just the first 2 and find the GCF, and you look at just the last 2 and you find the GCF, and then you take those matching binomials because it should be the same thing, what you have in parentheses, and you pull that out. You take it like another GCF. So I have 4 terms here. There is no GCF for all of them. If I look at the first 2, these have x squared in common. So I write that out. And then that leaves me with x plus 2 in parentheses. And then I look at the second 2 terms. These have negative 3 in common. So I'm going to divide both of those by negative 3. And then that leaves me with x plus 2. What you have in parentheses should match. If it doesn't, then this either doesn't work or you did it incorrectly. Since the stuff in parentheses matches, you write that stuff outside. And then you have another set of parentheses. You're basically taking the GCF out of both of these. So if I take out the x plus 2, I'm left with x squared. And then from the other term, I'm left with the minus 3. So your final answer is what you have inside parentheses and what you have outside the parentheses. And then this may be factorable more. You may be able to do like a difference of squares or something after that step. Second example, find what these numbers have in common here. So from looking at the first 2 terms, I'm going to take out 4v squared. And then 28 divided by 4 is 7. And v cubed divided by v squared is v. 16 divided by 4 is 4. And v squared divided by v squared cancels. And then do the same thing with this part. So these numbers are both divisible by negative 3, which will leave me with 7v plus 4. Remember, the stuff inside parentheses has to match, so if you get the wrong sign, just double check your work. Negative 12 divided by negative 3 was positive 4. So since my parentheses match, I write what's inside the parentheses and what's outside the parentheses separately. So now I have 4v squared minus 3. And remember, if you're not comfortable or not confident that your answer is correct, just FOIL it back out and make sure it matches your original question. So that's it for the factoring techniques we'll be using in this class. Thank you guys.